Okay, now summarizing what we just talked about. You got a magnet system, and you got the potential energy versus separation, which you got from previous experiment. You set up the beam with a couple of extenders on the end so that you can mount the small magnet far enough away from the metal that this magnet is not going to interact significantly with the metal of the rod. It doesn't have to be too awful far, and you can experiment. You can move that large magnet around in the vicinity of this distance and see how far you got to get from the end before it doesn't have any significant effect on the motion of the rod. Okay, so you're going to set it up now, and you're going to set up some dominoes in the large magnet so that you can release the system and begin timing it. So you release and take the data necessary to infer the angular velocity and kinetic energy right after release. And that's going to occur pretty soon after release. Now you've got a little distance in which the kinetic energy increases significantly. It doesn't increase instantly because the magnets keep repelling each other. But that repulsion drops off quite rapidly. So you deal with that. You figure out what the data you need is. I'll probably give you some hints. Also time the thing to rest, which means your timing is going to implicitly contain the angular displacement between release and rest. Okay. Now why does this thing, well, let's back up. Okay. Now let's go back to the idea of a single mass, M, at the end of a massless rod. And this is a distance, R. If we exert a net force here in such a way that the net force remains perpendicular to the rod, then the acceleration is just acceleration equals F net over M. So the angular acceleration is the acceleration over the radius something's very wrong with that, or the way I'm thinking about it. Give me a second. Okay, never mind, there's nothing wrong with it. Sorry, I should have thought that through before I started writing, before we started class, but I wasn't sure I was going to get to this, so I didn't really do that. Okay, apology. Okay, so you have this. Now clearly here I can multiply numerator and denominator by r, and this is what I get. But mr squared is just the moment of inertia of this system. So F net times R equals I alpha. Compare that with F net equals MA. Well, I, as you see from doing your homework, is analogous to a mass, and alpha is analogous to your acceleration in ways that I'll leave it to your homework to clarify, because we're almost out of time. We've got about 2 minutes. Both express Newton's second law. Call F net R the torque. And from these a notation, net torque equals F net R. It's net torque that accelerates a rotating system. Net torque equals I alpha, because we call this net torque now. This is Newton's second law for rotation, completely equivalent to Newton's second law, because we use Newton's second law to derive this. So if Newton's second law is true, this has to be true. And if this is true, we go backwards and say Newton's second law has to be true. They're totally equivalent, but they're applied in somewhat different situations. Net torque is moment inertia times angular acceleration. Now, net torque is calculated generally in a way that you're going to see, and I'm not going to get into today because we're out of time. Okay, we've got this. And it's the net torque due to the force of friction in the bearings of the rotating beam system that causes it to come to rest. So we'll close this with that's some friction, mostly in the bearings. It's got very good bearings because there's very little friction. But there is some because you see it coming to rest. There's also some air resistance, but we're going to kind of ignore air resistance We won't let it go too fast, and we won't put any sails on it that interact with the air, although we might do that later to get an idea of how drag works. Anyhow, the net force on the beam from friction is what primarily brings the system to rest. And can we calculate this from the data that we already have? Well, if we know the mass of the beam, we calculate the moment of inertia of the beam. I'll tell you, the mass of the beam I think is around 180 grams, but I'll tell you, I'll weigh one and tell you. The mass of the magnets, when we had magnets on the beam in our initial experiments, around 50 grams. I gave you all that information a long time ago, but I'll repeat it because I don't want you to have to go look it up. But we're going to be able then to calculate the moment of inertia multiplied by the angular acceleration and figure out how much torque is being exerted. Now we also noted, because of some curvature in the velocity, angular velocity versus time graph, that the angular acceleration is not constant. Maybe that's an indication that friction isn't constant. Maybe it's an indication that air resistance, while a minor contribution to the torque, does have a measurable influence and causes the curvature of the graph. It's all very interesting stuff, and we want to pull this whole system together and understand this, because if we do, we're going to have a pretty good overview of some of the most, probably 70% of the most important aspects of this entire course. Okay, well, that's where we're headed.